So far we have saw how trigonometry deals with compound angle. So let's see now how it deals with the scenario based on multiple and submultiple angles. Multiple and submultiple angles, in the sense, sine 2 theta, cos 2 theta, how the formula gets evolved from compound angles. So yes, let's see. Now sine 2 theta. Sine 2 theta can be written as sine of theta plus theta, right? So let's use sine of a plus b formula, which is sine a cos b plus cos a sine b. So literally sine theta cos theta plus cos theta sine theta is none other than 2 sine theta cos theta, which means 2s theta c theta sine 2 theta. Okay. Same way, and the formula sine 2 theta can also be extended equally. Okay, let's extend it. You would end up getting like wait on 2 sine theta cos theta, which is also equal to 2 tan theta divided by 1 plus tan square theta. You would get doubts why, how come this arrived. It's nothing but basically sine theta cos theta. Okay. Let's divide let's divide and multiply by cos theta. What we would get, sine theta divided by cos theta into cos theta the whole square. Am I right? So sine theta and cos theta can be written as tan theta, and cos theta the whole square can also be written as 1 by secant square theta, right? So tan theta divided by secant square can be written as 1 plus tan square theta. So in order to get 2 sin theta cos theta, we have to multiply 2 on both sides. So let's multiply 2. 2s theta c theta equal to 2 tan theta divided by 1 plus tan square theta. Hence, this is also equal to sine 2 theta. Okay. Same way, let's deal cos 2 theta, which is equal to cos of theta plus theta. Cos of a plus b is cos a cos b minus sin a sin b, which means cos square theta minus sin square theta, which can also be written in the form of 2 cos square theta minus 1 using the identity sin square theta plus cos square theta equal to 1 and substituting that in place of sin square theta. So we are getting it. And we can also write it as 1 minus 2 sin square theta. Putting the same identity, sin square theta plus cos square theta equal to 1, but in the place of cos square theta, like substituting in the place of cos square theta, and you're getting everything in terms of sin square theta. Okay. And we can also extend the same in tan also. 1 minus tan square theta divided by 1 plus tan square theta. Okay. So in this five different form, cos 2 theta can be written. So this is more very important to be noted, even this too. I'll put a very big box so that you can understand there are many different forms in which cos 2 theta can be written. Okay. We saw sin 2 theta, cos 2 theta, same way. Let's see tan 2 theta. Tan 2 theta is nothing but tan of a plus b. Let's substitute a as theta and b also as theta. We know that tan a plus tan b, tan theta plus tan theta divided by 1 minus tan a tan b. This is nothing but 2 tan theta divided by 1 minus tan square theta. Fine. And here there is a constraint where theta and 2 theta are multiples of pi by 2 or not, sorry, or not, or not multiples of pi by 2. Why? Because if they are multiples of pi by 2, this involves infinity, tan 90 equal to infinity, right? So the denominator wouldn't adjust properly and it would lead to invalid values, like indeterminate values, where you can't apply limit or like does not exist. So hence it is same way cot 2 theta. Cot 2 theta is equal to cot square theta minus 1 divided by 2 cot theta. Now you all saw how it behaves in terms of 2 thetas, something like that. And let's see how it behaves with 3 theta, sine 3 theta, cos 3 theta, tan 3 theta. First, sine 3 theta equal to 3 sine theta minus 4 sine cube theta. And cos theta is equal to 4 cos cube theta minus 3 cos theta. And tan theta equal to 3 tan theta minus tan cube theta divided by 1 minus 3 tan square theta. If you want the proof, you could use the same sine of a plus b formula where you can substitute a as theta and b as 2 theta. You would end up getting finally arrived answer as this. Okay. Then so we till now we saw how multiple angle get dealt in trigonometric ratio. So now let's see the submultiple angles. Submultiple in the sense the angle is dependent on its half angle, which means, for example, theta depends on theta by 2. This is popularly known as submultiples. And if theta depends on n theta, in the sense 2 theta, 3 theta, 4 theta, it is called multiples. So let's see how the ratios behave. So now let's put how sine theta behaves. So we all know that from the equation sine 2 theta, sine 2 theta equal to 2 sine theta cos theta, right? So substituting theta as theta by 2. So we would get sine of 2 of theta by 2, which is equal to 2s theta by 2 c theta by 2, which means 2 sine theta by 2 cos theta by 2. So hence sine theta can also be written as 2 sine theta by 2 cos theta by 2. That's the thing. Same way, you can substitute in all in all the identities. 2 tan theta by 2 divided by 1 plus tan square theta by 2. Okay. So this is also one more identity. Same way, cos theta. Substituting the same thing where you'll be substituting theta by 2 instead of theta. So cos theta would be cos square theta by 2 minus sine square theta by 2, which can also be written as 1 minus 2 sine square theta by 2. This is minus 2 c square theta by 2 minus 1. Okay. Same way, we could also extend it up in terms of tan t square theta by 2, 1 plus t square theta. So yes, we all dealt with. Let's put a big box. Now let's solve again in the same way. Tan theta equal to 2 tan theta by 2 divided by 1 minus t square theta by 2. Just substituting. Okay. So these are the identities, and let's now see further angles to be noted. Let's develop the degree ratio table, degree table for furthermore angles other than 0, 30, 45, 60, and 2. So now let's develop it for 18 degree, 36 degree, 54 degree, and 72 degree. It's very important. Theta, cos theta. Okay. Sine 18 is root 5 minus 1 by 4 Same way, cos 72 is root 5 minus 1 by 4. And sine 36 is root 10 minus 2 root 5 by 4. Cos 54 is same. Here root 5 plus 1 by 4. Root 5 plus 1 by 4. Okay. Then you will be asking what about 74? Yeah, I'll tell you the same. Here instead of minus, you will be getting plus. Okay. So this is for 18 degree, 36, 54 and 72. And if you want, even you can extend it up for 22.5 or 67.5. Sin theta, cos theta. 22 1 by half and 67 1 by half. You could get like doubts how you are tabulating these values. Yes, I will tell you how I tabulated it. Using the submultiples and multiples, I am tabulating these values. You would get a question how. So, see, 22 and a half degree is nothing but 45 divided by 2. So, I would just substitute sin theta is equal to 2 sin theta by 2 cos theta by 2. So, sin 45 is popularly known as 1 by root 2, right? So 1 by root 2 is equal to 2 sin theta by 2 cos theta by 2. Same way, I also substitute cos theta here. Cos 45 is equal to cos square theta by 2 minus sin square theta by 2. And I develop and I solve this equation and I would end up getting sin theta by 2 value. And then we all know that sine of 90 degree minus theta is equal to cos theta. So you would be getting the reverse. If sine 22 and a half I got, I would get cos 67 and half. And same way, if I get sine 67 and half, I would get cos 22 and half. So in that way, I'm developing this table. So, sine 22 and half is really a huge value to remember, but it's just for how I am using this identity, just for demonstrating that I am telling root 2 minus 1 by 2 root 2. Anyway, you guys have a calculator for getting these values. Still, same way, sine 67 and half, I can write it as like sine of 135 divided by 2, or else I could use even sine sine 3 theta identity. Why? Means I have theta as 22 and half, and 3 into 22 and half would end up getting 67 and half. So in that way also I could get the value. So for this, the same thing, but with plus 1. You would actually analyze there exists a pattern in this. See, 22 and half, 45, 67 and half, and 90 are equal intervals, right? So here, for sine theta, you end up getting root 2 minus 1 by 2 root 2, and here, wait, root 2 minus 1 plus 1 by 2 root 2. Here minus 1 and plus 1 exists, so here definitely it should be plus 0. So let's solve it. Root 2, I am putting root 2 by 2 root 2. And same way here you will be getting 2 plus root 2 divided by 2 root 2. So that that value amounts you to get 1. Yes, see. root 2 and root 2 is cancelled, and you will get root of 1 by 2, which is 1 by root 2. Yes, the value is satisfied. So you could develop the thing as this is theta and theta by 2, and then 3 theta by 2. So in that way, you would adjust the identities and you could formulate the values, substitute the values, and you can end up getting any number of degree. For any degree, you could get the value from sine 1 to sine 360. Whatever you can adjust using the identities. Maximum till 4 theta, we could able to derive the identities, and with that, if you substitute the required particular angles, you would end up getting the values of almost all the degree from 1 degree to 360 degree. And if you get the sine, you could reverse that in descending order, you would get up the cos. And same way, if you divide the sine and cos, you would get tan. Similarly, you could derive all other ratios, cosecant, secant, and cot, by taking reciprocals of sine, cos, and tan respectively. So let's see numericals in next episode based on these identities. That would be really interesting and it won't bore you, and there are like more number of surprises hidden where we will be coming across more number of equations, and it would be really nice. Please like, share, and subscribe.